We are the VTT iBEX 22 team, spider spindles, and our mission is to create this nanocellulose thread that can be utilized as a surgical suture, and it is created with the help of microfluidics. How this microfluidics works is that we have the nanocellulose coming in there, and we are utilizing this flow focusing with the help of the microfluidics and combining it with other reagents that allow the formation of the nanocellulose thread with the functional groups. And then we can produce the thread, and it's used as surgical suture that can be used to connect the cut nerves. And then this thread will eventually biodegrade inside the patient, and it contains the growth factors that are increasing the speed how the neural damage is repaired.
Eli me keskitytään tähän nyt sitten tässä projektissa laivaliikenteen hiilidioksidipäästöjen vähentämiseen. Ja jos katsoo niin laivan liikennöijä tai omistaja, laivan omistaja, niin vaihtoehto siinä, niin se on käyttää uusiutuvia polttoaineita polttomoottoreissa tai sitten alkaa sähköistämään. Ja sähköistämisessä niissä meillä on akut tai polttokennot, mutta isoimmissa laivoissa niin akkuja ei enää pysty käyttämään, koska niitä on liian paljon tai tarve on niin iso, sitten on polttokennot. Ja tässä on vähän eri polttokennoteknologioita, joista me ollaan nyt valittu kiinteäoksidipolttokennot, korkean lämpötilan polttokennot, jossa on korkea hyötysuhde. Ja tässä sitten niin eri mahdollisia polttoaineita näin tulevaisuuden meriliikenteen kannalta. Ja meidän projektissa sitten ollaan keskitytty ammoniakkiin ja ammoniakin käyttö sitten juuri tässä kiinteäoksidipolttokennossa, sen niin teknologinen käyttö mahdollistaminen.
So our project name is Biocatechol, and our goal is make more chemicals out from plant biomass. And the biomass, which is represented here, the wood. So there are two major components. One is cellulose, from which there are already a range of products, chemicals, fibers, fuels can be made from cellulose. The other part is aromatic polymer ringing, and that is the tricky part, and that is the one where we focus on.
Okay, so this brown stuff here, that is the lignin, and that is often just burned because there's not so much use for it. So in nature there are the fungi or mushrooms which can use lignin. They are called white-rod fungi. And we will then take these mushrooms into a bioreactor and also the lignin, and there the white-rod mushroom is not using the lignin for growth, which is naturally doing, but we have genetically engineered it so that it will then make some aromatic compounds out of it.
And then we can take this aromatic compound, here we have a catechol, and then we're going to turn it to a dyes, for example, some kind of indigo derivatives and pharmaceuticals.
Eli meidän projektimme nimetään DAKU. Rakennetaan tällainen reaktori, jossa on polymeeriketjuja, jotka absorboi ilmasta hiilidioksidia. Siinä on myös laitettu katalyyttiä. Ja sen lisäksi me tarvitaan uusiutuvalla energialla tuotettua sähköä, jolla me voidaan hajottaa vettä vedyksi ja yhdistää sen meidän absorboituneen hiilidioksidin kanssa tehty polttoainetta. Ja tämä on tarjonnut vaihtoehtona tämmöiseen perinteiseen saastuttavaan teollisuuteen, joka aiheuttaa nyt meidän pahoja ympäristötuhoja. Että meidän projektin ideana on paitsi ottaa ilmasta pois hiilidioksidia, niin myös tehdä sitä hiilidioksidia jotain hyödyllistä, tässä tapauksessa esimerkiksi polttoaineita tai vahoja.
In our project, we want to turn plastic waste of polyolefins, or polypropylene, polyethylene, polystyrene, into fatty acids, which is here so much soap, by conversion. So the idea is that we take a plastic waste fraction that would otherwise go into burning. Do some pre-processing in that reactive extrusion to make the plastic waste more hydrophilic. The next step is incubating with a yeast which produces enzymes that can digest alkynes and alkanes into fatty acids.
Eli me ollaan iBEX Force Nature Team. Olen yksi jäsen tästä tiimistä. Ja mitä me tehdään on siis, että me yritetään tuottaa lihan kaltaista tai lihan muistuttavaa ruokarakennetta, mikä on koostuu useista komponenteista ja missä käytetään siis mikrobeja, lähinnä hiivoa, erilaisia hiivoja tuottamaan lipidejä, sitten makuja ja värejä ja proteiineja. Ja näistä saataisiin semmonen rakenne, mitä voidaan sitten bioreaktoreissa tuottaa ja sitten syödä.
So this is Team Boomerang, and our aim is to develop coating materials that could replace plastic in many of our everyday products. We aim to develop barrier material, coating material, exploiting microbial cells. So here you can see
The microbes.
our microbial cells growing in a fermenter, and we are producing fatty acids inside the cells.
Yeah.
So they are, you can see them inside those capsules. And after we have been producing sufficient amount of our microbial cells, we take the cells to a mechanical disruption. So the aim is to break the cells and liberate the polymers that we have inside the cells. And after the mechanical action, we take the components that we get from the cells, we process them in nice ways, and find a perfect way to formulate a coating based on the microbial cells. And there we have the fatty acids that bring the hydrophobicity for our coating, and these blue things represent cell walls of the microbes.
Our project is about developing a method to measure the origin of emission of CO2, and this is important because currently producers of CO2 have to pay taxes, and you pay taxes, for example, only if it's fossil emission. And of course, as the carbon prices goes up, to be even more important to only pay for the real emission you are doing, and not only based on an estimation. But also, if you start capturing the CO2 you are emitting and using for other products, you can actually sell the biogenic CO2 at a higher price than the fossil one, meaning that company can make more money by producing more biogenic CO2. So by having a good measurement method, they can then certify that their CO2 is 80% biogenic, for example.
We are Team Cool Cellulose, and we are focusing on radiative space cooling films made from bio-based materials, and in this case it's cellulose derived from the forest. You can see just behind this house, and here we have a prototype of a house that has two different segments. One where there is just a conventional roof, no passive cooling system, and there could be, for example, in the case of heat waves, very severe health issues related to that. And then on the other side we have the cool cellulose film, which helps us cool our buildings and spaces using much less energy as compared to the conventional sources like air conditioning. And also we are building adaptive cooling systems here so that they don't cool when cooling is not needed anymore. For example, in winter we actually then heat the space using the same material, and it adapts automatically to the changing climatic conditions.
So we are from RE-free team. So RE-free stands for the rare earth element free magnet. We want to develop a new material, new magnet which has no rare earth element, and this starts from by combination of various disciplines. We start from the computational material simulations, which allow us to try to tailor the crystal structure in a way that we can provide a guideline to the processing route. What would be the suitable solution? What would be the suitable compositions that the process viewer has to add, and then this means they can produce this. And with this way, at the end, we'll try to test it within this project, try to produce this this material, this rare earth element-free magnet.